Hello, I'm Norman Wildberger. Last time we started thinking about polynomials in terms of sequences rather than as functions. Today we're going to continue with that, and we're going to talk about Stirling numbers, which come about when we look at the change of basis between ordinary powers and rather special powers that we introduced last time. We're going to see that there's a natural connection between these Stirling numbers and matrices that we can make from them and Pascal triangles. First, I need to change my terminology a little bit, I think. So last time we had a look at these two kinds of polynomials. So alpha to the n falling is alpha, alpha minus 1, alpha minus 2, alpha minus n plus 1. A product of n terms starting with alpha, each one less. So let's call that a falling power instead of a lowering power. And alpha to the n rising, alpha, alpha plus 1, alpha plus 2, all the way up to alpha plus n minus 1. Again, there are exactly n terms starting from alpha. Let's call that a rising power. Instead of last time I called them raising powers. All right, so just a little bit of change of terminology there. I think this is somewhat more standard. Okay, so let's have a look at these two kinds of polynomials today. And there are some very interesting numbers that arise from them. And the numbers arise in a very simple way. For example, if we take the rising powers and we expand them out and have a look at the coefficients, we get some interesting numbers. Okay, let's start with 1. That's the first one. Of course, that's just equal to 1. Alpha to the 1 rising is the same as alpha. Alpha to the 2 rising is alpha times alpha plus 1, which is alpha squared plus alpha when we expand it. And here's alpha to the 3 rising. Alpha times alpha plus 1 times alpha plus 2. You expand it out, you get alpha cubed plus 3 alpha squared plus 2 alpha. Here's alpha to the 4 rising. We get coefficients 1, 6, 11, and 6. And here's alpha to the 5 rising. We get coefficients 1, 10, 35, 50, and 24. So there are interesting numbers that are appearing here. And of course, we can carry on. We're interested in the sequence of rising powers. So we can express the coefficients compactly with this summation notation by saying that alpha to the n rising is a sum from k equals 1 to n of a certain coefficient, which we'll call n bracket k, times alpha to the k. So in this sum, we're starting with the lower powers of alpha and going up in the powers of alpha. So for example, here's alpha to the 5 rising. Then, in terms of this sum here, we would start with alpha. So this would be 5 bracket 1. This would be 5 bracket 2, 5 bracket 3, 5 bracket 4, and 5 bracket 5 would be 1. These numbers here, these bracket numbers, are called Stirling numbers, or more precisely, Stirling numbers of the first kind. Now you could say, well, what about the falling powers? We could do the same thing for the falling powers. For example, here's alpha to the 5 falling. Alpha times alpha minus 1 times alpha minus 2 times alpha minus 3 times alpha minus 4. When you expand that out, you get something that's very similar to alpha to the 5 rising. There it is right there. The difference is that every second term has a minus sign in front of it. But otherwise, the coefficients are exactly the same as for alpha to the 5 rising. So once we know how to expand alpha to the n rising, we can also very quickly figure out what is alpha to the n falling. Okay, so let's have a look at these Stirling numbers in some more detail. Stirling numbers were introduced by James Stirling in 1749 in a work called Methodus Differentialis. There are quite a lot of different notations for Stirling numbers in the literature. One must be a little bit careful, I warn you. We're going to follow Donald Knuth in using the notation with a bracket. So n bracket k, that's going to be our Stirling number. That's sometimes called Karamata notation, after a Serbian mathematician who introduced it. So to rewrite what we did on the previous board, what we really have going here is a change of basis. So we have one basis consisting of the rising powers and another basis consisting of the ordinary powers, say in this case up to degree 5. And we have a way of representing each rising basis as a linear combination of the standard basis. So what this is saying, for example, is that the fourth rising power is 0 times 1 plus 6 times alpha plus 11 alpha squared plus 6 alpha cubed plus alpha to the fourth. So this row right here is telling us how to express alpha to the fourth rising in terms of our usual standard basis of our polynomials. And this matrix here that represents the various Stirling numbers, we'll call that a Stirling matrix of the first kind. And we note that the indexing is such that this element here, for example, that's 5 bracket 2, that's actually in the row indexed by 5 when you start counting by 0. 0, 1, 2, 3, 4, 5. And it's only in the column indexed by 2 if you start counting by 0. 0, 1, 2. So when we are talking about these Stirling matrices with the bracket notation, we have to remember that our indexing starts with 0. It's a little bit unconventional, but it's not that unusual. The Stirling numbers are best calculated by using some kind of recurrence. We don't actually have a very good formula for them as such, but there is a very useful recurrence that connects them very closely to the Pascal triangle or the binomial coefficients. To see what that recurrence is, let's have a look at how we actually would calculate these rising powers in terms of previous rising powers. So here is alpha to the 3 rising, 2 alpha plus 3 alpha squared plus alpha cubed, and I've written it now with increasing powers of alpha. And here's alpha to the 4th rising, 6 alpha plus 11 alpha squared plus 6 alpha cubed plus alpha to the 4th. And let's think about how we would get this one if we knew this one. Well, kind of obviously what we're doing is we're taking the 3 rising polynomial and we're multiplying it by alpha plus 3. So what does that mean? Well, it means that we have to multiply this first by alpha and then by 3 and add them together. So I've shown you that here. I've shown you that if we take alpha to the 3 rising here and multiply it by alpha, we get 2 alpha squared plus 3 alpha cubed plus alpha to the 4th. And I've just written it here so that we're underneath the same powers of alpha as above. And now I'm adding 3 times the same polynomial, so 3 times this one here. 3 times 2 alpha is there, plus 3 times 3 alpha squared, plus 3 times alpha cubed. And then what we see is that this 6 is really the sum of the 2 things below it, the 3 plus the 3. The 1 is equal to 1. This 11 is the sum of 2 plus 3 times 3. The 6 is equal to 3 times 2. So another way of saying it is the 11, which is 4 bracket 2, that one there is obtained by looking at 3 bracket 1, which is the term 2, plus 3 times this 3, which is 3 bracket 2. So this is a special case of a more general fact. And here is the general recurrence of which this is a special case. It's that n plus 1 bracket k is equal to n bracket k minus 1 plus n times n bracket k. And the proof of it is obtained by staring at really just this formula. That alpha to the n plus 1 rising is alpha to the n rising times alpha plus n. So if you want terms here, what you do is you take the terms here and you do two things to them. You multiply them by alpha and you multiply them by n, and you combine those two to get the terms here. So multiplying by alpha, it's giving us these coefficients, and multiplying by n, that's contributing this term here. When we add them together, we get the kth term over in this one here. So please have a look at this, stare at this, work out some special cases to convince yourself of the truth of this recurrence relation. And hopefully it's very familiar looking. It looks a lot like the standard recurrence relation for the binomial coefficients. So let's have a look at Pascal's triangle and binomial coefficients from the viewpoint of polynomials and linear algebra. The way we get the binomial coefficients and Pascal's triangle is to look at powers of alpha plus 1. So if you expand alpha plus 1 to the fourth, then you get 1 times 1 plus 4 times alpha plus 6 times alpha squared plus 4 times alpha cubed plus 1 times alpha to the fourth. So these coefficients can be interpreted as simply a way of writing this polynomial in terms of this basis. In this case, of all the polynomials of degree 5 or less. So here I've shown you all the polynomials of degree 5 or less, powers of alpha plus 1 in terms of the standard polynomials. And you'll recognize Pascal's triangle, I hope. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. It's not exactly written as a triangle like this. It's now written as a triangle with a left justified side. But it's still the case that this plus this equals this. That every term is the sum of the term above it and the term above it to the left. So the entries in this table are called binomial coefficients. We're also labeling them in the same way as we did the Stirling numbers. So we're thinking of our rows as starting from row 0, row 1, row 2. So this would be row 5. And thinking of our columns as being indexed by column 0, column 1, column 2. So this would be 5, choose 2. It's in the 5th row and in the 2nd column. These are called binomial coefficients. And they satisfy this recurrence relation that n plus 1 choose k equals n choose k minus 1 plus n choose k. Exactly the same as the one for the Stirling numbers of the first kind, except that there's no n rate sitting there. And it's because of the parallel between the binomial coefficients and the Stirling numbers that we choose that bracket notation to represent the Stirling numbers, to bring out the similarities between the Stirling numbers and the binomial coefficients. This matrix here we'll call a Pascal matrix. So the whole matrix captures part of the what's usually called Pascal array. Of course, we can do this not just for 5, we can do this for 6, 7, or any number. And we get bigger and bigger Pascal matrices. But the Pascal matrices for the smaller ones are contained inside the bigger ones. So that one there would be the Pascal matrix if you went up to degree 3, for example. One of the reasons why Stirling numbers are interesting and important is because they have a combinatorial interpretation. N bracket k has an alternate incarnation as a combinatorial number. It's the number of permutations of the set 1, 2, up to n with exactly k cycles. So let me try to explain briefly what that means. With an example, let's look at 4 bracket 2, which we know is 11. According to this is counting the number of permutations of the set 1, 2, 3, 4 with exactly k cycles. So what is a permutation of, say, the set 1, 2, 3, 4? Well, you just imagine you have 4 people or 4 objects, and permuting them means you're just moving them around. You're taking one and putting that person in another person's place, and that other person is put into another person's place. So the 4 people are changing their positions. And there are lots of ways of doing that. Here's, for example, one way. We could move person 1 into person 2's place and person 2 into person 1's place. So essentially ask 1 and 2 to change places, and at the same time ask 3 and 4 to change places. That would be one possible permutation. And this is a permutation with 2 cycles. A cycle being what you get when you start with one person and see where that person would go, and then if you did it again, where would he go again, until you close back to where you start. Then that's called one cycle. So here there are exactly 2 cycles. Here's another permutation, a different one, which also has 2 cycles. We agree to interchange 1 and 3 and 2 and 4. Here's another one, interchange 1 and 4 and 2 and 3. That also has 2 cycles. But there are a couple of other ones that have 2 cycles of a different kind. So have a look at this permutation. This permutation is the one where person number 3 is staying where he is. Okay, not everything has to move when we permute. And person number 1 goes into 2's spot, person number 2 goes into 4's spot, and person 4 goes into person 1's spot. So these 3 cycle around. Person number 3 is stationary. So this particular permutation also has 2 cycles. There's the 1 cycle there, and 3 by itself is another cycle. And it's not too hard to count that there are exactly 8 permutations that look like this one. So for example, we could also permute 1, 2, and 4 in the opposite direction. That's counted as a different permutation. Or we could choose, say, 4 to sit out and permute 1, 2, and 3, or have 2 sit out and permute 1, 3, and 4, and so on. So there's 8 of that kind, 3 of this kind, a total of 11 permutations of 4 objects with exactly 2 cycles. And that's the combinatorial interpretation of the Stirling numbers. We also have a number theoretical interpretation of the Stirling numbers. Let's have a look at that. So n bracket k is also the sum of all products of n minus k elements from the set 1, 2, up to n minus 1. What does that mean? Let's illustrate it in an example. Suppose that we're looking at 4 bracket 1. That would be the sum of all the products of 4 minus 1, in other words 3, elements from the set 1, 2, up to 3. Okay, how can you choose 3 elements from the set 1, 2, 3? There's only one way. You have to choose them all. And there's that product. There's only one product. It's 1 times 2 times 3, so that Stirling number is 6. What about 4 bracket 2? So now we're talking about the sum of all products of 4 minus 2, or 2 elements from the set 1, 2, 3. So we need to take 2 elements from the set 1, 2, 3. 1 and 2, 1 and 3, 2 and 3. And we form all the products with those 2 elements. So 1 times 2, 1 times 3, 2 times 3, and we add them together to give us 11. What would 4 bracket 3 be? That would be the sum of all the products of 4 minus 3, in other words, 1 element from the set 1, 2, 3. So there are 3 possible products that we could take. Just the singleton 1, just the singleton 2, just the singleton 3, and there's the sum. It's also 6. A bit more complicated example, say 5 bracket 2. That would be the sum of all products of 5 minus 2, or 3 elements from the set 1, 2, 3, 4. So if you have the set 1, 2, 3, 4, how many ways are there of taking 3 elements? Well, there's 4 ways. You could take 1, 2, and 3. You could take 1, 2, and 4, 1, 3, and 4, and 2, 3, and 4. And for each one of those ways of taking 3, you multiply the 3 together, form a product. So 1 times 2 times 3, 1 times 2 times 4, 1 times 3 times 4, 2 times 3 times 4. and you form the sum of those products, that's the Stirling number. Why is it true? It's in fact almost obvious when you look at what the rising power is. So alpha to the 5th rising. I remind you, it's alpha times alpha plus 1 times alpha plus 2 times alpha plus 3 times alpha plus 4. And here it is written out in terms of the various Stirling number coefficients. So let's have a look, for example, at 5 bracket 2, this 50 that's appearing. It's the coefficient of alpha squared when you expand this out. So ask yourself, how can you get an alpha squared when you expand this out? Well, there are 5 terms. So what you're allowed to do is you're taking an alpha from one of the terms and an alpha from another term, and the other 3 terms you have to make sure you're not taking an alpha, because we want just alpha squared. So in fact we have to take that alpha, and then we can take one of these other alphas, say that one there, and so what we're doing is we're then multiplying these 2 terms with the non-alpha terms in the remaining 3. In this case 1 times 3 times 4. And so if you think about what that is, you can see that the coefficient of alpha squared will just be this sum. The sum over all the ways of picking 3 things from these 4 terms, multiplying those 3 things together, 1 times 2 times 3, or 1 times 3 times 4, and adding them all together. That's a rather general reason why this interpretation exists. Okay, so we have the original definition of Stirling numbers in terms of essentially a change of basis between the rising powers and the ordinary powers of polynomials. We have a combinatorial interpretation in terms of numbers of permutations with a certain number of cycles. And we have this number theoretical interpretation in terms of a sum of products of a certain kind. Now, at various stages in history, each of these different interpretations was considered the most prominent one. But I think now that the dust has settled, it's really the first definition which is the most fundamental and the best one. Okay. The definition in terms of rising powers expressed in terms of standard powers. And in fact, that's exactly what Stirling's original orientation was. So the interpretation in terms of combinatorics, in terms of these sums of products, they came after Stirling. Stirling was interested in how you write out a rising power in terms of ordinary powers. And that's the linear algebra point of view. It's really a change of basis from one kind of basis to another kind of basis. So I've mentioned that there are also these other types of Stirling numbers, the Stirling numbers of the second kind. How do we get them? To motivate that, let's have a look at the Pascal matrices again and ask about how we invert a Pascal matrix. So let's stick with the degree 3 or less case. So here are the standard basis elements of our space P3, 1 alpha, alpha squared, alpha cubed. Here are some shifted basis vectors, maybe we call it Taylor basis, 1 alpha plus 1 squared, alpha plus 1 cubed. And this is the Pascal matrix that tells us how to express one of these polynomials as a linear combination of those polynomials. So I remind you what the fundamental problem in linear algebra is. The main motivating problem is how to invert such a linear relationship. How do you express these polynomials in terms of these polynomials? That's the problem of inverting this matrix. And in this case, there's a little bit of a trick that one can do to minimize the amount of work. The trick is to first of all have a look in this equation here and replace alpha plus 1 by alpha minus 1. So if we do the same thing with alpha minus 1 instead, powers of alpha minus 1, then we get the same kind of binomial coefficients but with some minus signs thrown in. So for example, if you take alpha minus 1 cubed, then you're going to get alpha cubed minus 3 alpha squared plus 3 alpha minus 1. So it looks much the same as this one, except that on the diagonals, there's a plus sign on all of those, a minus sign on all of those, plus and minus. Okay, so what do we do now with this thing? Now with this thing, we just replace alpha by alpha plus 1. So alpha plus alpha goes to alpha plus 1. So this becomes alpha squared, this becomes alpha cubed. This matrix stays where it is. And these terms over here become alpha plus 1 squared, alpha plus 1 cubed. And we've got exactly the original basis vectors in terms of the Taylor basis vectors over here that we wanted. We've inverted this relationship to get this one. So we can conclude that the inverse of this matrix, the inverse of that matrix, is in fact this matrix. It's a lot less work than inverting matrices usually is. Usually inverting matrices is quite a lot of work. Here what we do is we just take the matrix and we put minus signs down that diagonal, and then skip a diagonal and put minus signs down the next diagonal. And if it was a much bigger Pascal matrix, the same recipe would hold. We would leave the diagonal where it is, and then the next diagonal below that we would multiply all of them by minus 1s. Leave the next diagonal by itself, the next ones by minus 1s, and so on. So we want to ask the same question now for the Stirling matrices. Okay. What happens when we try to invert a Stirling matrix? That turns out to be not quite so simple as with the Pascal story. Okay, so let's have a look at an example to see what happens when we invert a Stirling matrix. So here's our favorite case of degree 3 or less polynomials. And here are our rising powers expressed in terms of our standard powers. And here's the Stirling matrix that does that conversion for us. So you can compute what the inverse of this matrix is. Okay, and I've computed it there for you. And although it has roughly a similar kind of shape to the original, it is different. This one was a lower triangular matrix. This one is also a lower triangular matrix. This first row here had a 1 and then a bunch of zeros. This first row also has 1 and zeros. Although the diagonals are still 1s, these off-diagonal terms seem to be a little bit different from these ones here. Although we do notice that there's some minus signs along this diagonal and no minus signs there. But it's certainly not clear what the pattern is. If we went to a bigger size, how would we generalize this? Now, at this point, it's important for me to reintroduce some symmetry that I've been kind of ignoring. Today I've been talking about these rising powers. But we've seen that the falling powers are just as important. So the entire discussion that we've been doing could also have been restated in terms of the falling powers. So we could have started out by asking, how are the falling powers related to the standard powers? And I told you that on the first slide. I showed you one example that essentially we're getting the same matrices as the Stirling matrices, except that there's some minus signs in exactly the familiar places that we're getting used to now, on the diagonal below the main diagonal, and then skip one, the next diagonal. So the minus signs alternate, plus, minus, and so on along every row. So this is falling powers in terms of standard basis. This is rising powers in terms of standard basis. So now let's ask, how do you invert this particular matrix? Well, you can do the calculation again. So you end up expressing the standard powers in terms of the falling powers. And the matrix that you get is, perhaps not too surprisingly, quite connected with this one. In fact, it's simpler than this one. It's exactly the same thing as this one, but there are no minus signs. So it's important to look at all of these four matrices, I think. So here are the Stirling numbers of the first kind encoded in a matrix. There's the inverse of it. Here's another matrix that we haven't looked at that much, and its inverse is this. These two are pretty well the same, except for minus signs along suitable diagonals. And these two are also pretty much the same, except for minus signs on suitable diagonals. This matrix has all positive entries. This matrix has all positive entries. So these matrices here are particularly pleasant. I'm going to call this one here the Stirling matrix of the second kind. And the entries of this matrix are going to be the Stirling numbers of the second kind. So the Stirling numbers of the first kind are obtained by expressing the rising powers in terms of the standard powers. The Stirling numbers of the second kind are obtained by expressing the standard powers in terms of the falling powers. So there's some pleasant symmetry there. So let's have a look at these Stirling numbers of the second kind. So our definition of these Stirling numbers of the second kind, which we call n brace k, and we denote with these brace kind of brackets, is this. We write alpha to the n as a linear combination of the falling powers alpha to the k, falling, from k equals 0 to n. And whatever coefficients we need to make that work, those are the coefficients n brace k. So for example, here's the case when n is equal to 5. Each one of these rows represents an expression for a power of alpha in terms of the falling powers. So for example, alpha to the 4th is 0 times 1, 1 times alpha 1 falling, 7 times alpha to the 2 falling, plus 6 times alpha to the 3 falling, plus 1 times alpha to the 4 falling. And our notation is the same as it was for the Stirling numbers of the first kind. We index our rows by 0 first, and then 1, 2, 3, and so on. And similarly, the columns indexed by 0 first, then 1, 2, 3, and so on. So this element here, being in the row indexed by 4 and the column indexed by 2, is the 4 brace 2 term. So 4 brace 2 is equal to 7. That's 4 brace 3, 4 brace 4, and so on. And this thing here, we'll call this a Stirling matrix of the second kind because it's made up of Stirling numbers of the second kind. And we can make such a matrix for any n. And in particular, they all are kind of nested inside each other. So the one for n equals 3 would just be that portion of the one for n equals 5. There's really a kind of an infinite array that represents all the Stirling numbers of the second kind. And just as for the Stirling numbers of the first kind, there was a combinatorial interpretation, we also have one for these Stirling numbers of the second kind. N brace k turns out to be the number of partitions of n objects into k non-empty subsets. Well, what does that mean? We'll think of the n objects as being the numbers from 1 to n. And what we're trying to do is we're partitioning that set. In other words, breaking it up into sub-pieces, disjoint subsets that fit together to form the whole thing. That's what a partition is. And we're interested in counting the number of elements in this partition. How many different blocks are there? So we're interested in how many partitions of n have exactly k pieces or k non-empty subsets. So for example, 4 brace 2 is 7 because the number of partitions of 4 into exactly 2 subsets is 7. And I've listed them here for you. So here's one partition. We break the numbers into one subset containing 1, 2, and another subset containing 3, 4. Or another way would be choose the subset 1, 3, and also the subset 2, 4. Or 1, 4, and 2, 3. But there are a few others. We could also break them up into a subset with 3 elements and one with just 1 element by itself. And there are 4 of those. Altogether, 7. Now, just as for the Stirling numbers of the first kind, the Stirling numbers of the second kind also satisfy a recurrence relation. And it's very much the same as the one for the Stirling numbers of the first kind, and almost the same as the one for the binomial coefficients in Pascal's triangle. It's n plus 1 brace k equals n brace k minus 1 plus k times n brace k. For the Stirling numbers of the first kind, this k was an n. And for the binomial coefficients, this number was just 1. So the three different numbers, the binomial coefficients, the Stirling numbers of the first kind, and the Stirling numbers of the second kind, are all pretty close when it comes to their recurrence relation. However, one difference, a big difference, is that the binomial coefficients have an exact formula that allows you to calculate them pretty efficiently. Calculating the exact values for these Stirling numbers is more tricky, and usually one has to involve a recurrence. So this kind of relation is actually quite important to compute Stirling numbers. For us, the importance of the Stirling numbers is that they represent going from one basis of our space of polynomials to another basis of our space of polynomials, when we're thinking of the polynomials as representing sequences. So let's have a look at our favorite example, our space of polynomials of degree 3 or less, called P3. And here's a familiar basis, the basis of just ordinary powers. The standard basis, we'll call that B, consisting of 1 alpha, alpha squared, and alpha cubed in that order. And now let's denote F for falling, the basis of falling powers, 1 alpha, alpha to the 2 falling, alpha to the 3 falling. These are also polynomials. So here's the relationship between the standard basis of P3 and this falling basis of P3. And here's the matrix of Stirling numbers of the second kind, the ones we've just been looking at. And over here is the inverse situation, where we've inverted this linear system, expressing the falling powers in terms of the standard powers. And you may recall that this matrix here was essentially the matrix of the Stirling numbers of the first kind, except that there were some minus signs appearing on certain diagonals. Okay, now a very interesting question here is, how does this kind of change or relationship between the bases, how does that translate to a relationship between coordinate vectors for a particular polynomial? It's a very important question. So what I have in mind is this. Suppose we have a particular polynomial in P3. We can express that polynomial with respect to this basis, or with respect to this basis, or in fact with respect to any basis that we want. But we're just considering these two for now. So suppose that when we write P in terms of the B basis, the coefficients are A0, A1, A2, and A3. So that's just the ordinary representation of the polynomial the way we usually write it. These coefficients in a vector form the coordinate vector for the polynomial with respect to the basis B. And we'll write this. This is a coordinate vector of P with respect to the basis B. It's actually a vector of 4 numbers representing the 4 coefficients. If we change the basis from B to F, then we have to change the coefficient vector. We're now talking about 4 new numbers, so that P is B0 times 1 plus B1 times alpha plus B2 times alpha to the 2 falling plus B3 times alpha to the 3 falling. In other words, the coefficients of P when we express it in terms of a linear combination of these basis vectors. So this is now a very standard problem in linear algebra, where you have 2 different ways of looking at things, and you have a coordinate vector for some object with respect to one basis, coordinate vector with respect to another basis, and we want to know, what is the relationship between these two? How do we go from one of these to the other? Well, obviously it should be connected with the matrices that are involved here, because these matrices are telling us how to go from the basis vectors in one system to the basis vectors in the other system. Now this kind of problem goes right back to our first few lectures in this course, when we talked about Bob and Rachel, you may remember. Perhaps that was the second lecture. We talked about Bob's basis and Rachel's basis, and how to go from Bob's basis to Rachel's basis, how to express Bob's vectors in terms of Rachel's vectors, and so on. And then how to go from Bob's representation of a particular vector to Rachel's representation of that same vector. Might be a good idea for you to have another look at that, because we're going to have a look at that situation now in this situation where we have these bases of these polynomial spaces. In fact, we're very interested much in exactly the problem for these two particular bases. So how do we answer this question? In practical applications of linear algebra, this question that we're talking about now is of primary importance. It comes up in many, many different situations. And most textbooks slight this subject because most students find it a little bit hard. It's easy to get confused about what's going on when you change bases from one basis to another of a linear space. But in practice, it's something that we often do. It's one of the main applications of linear algebra, because it's directly connected to that primary problem of how to invert a linear change of coordinates. So I'm going to introduce a little bit of non-standard terminology and ideas here, which are not found, I think, in any standard text. And I think these ideas help students to understand what's going on, although we're using our notation in a slightly novel way. So I maybe have to flag this. Let's have a look at our polynomial p. And here's the polynomial written out in the standard fashion. Now, when we look at this, we see a bunch of sums of products between numbers and vectors. So this number times that vector, plus this number times that vector, plus this number times that vector, plus this number times that vector, where the vectors in this case are the polynomials. Well, that kind of expression is the same kind of thing that we get when we multiply a row vector by a column vector using matrix multiplication. If these were ordinary vectors of numbers, then this product would be a 1 by 1 matrix whose terms would be 1 times a0 plus alpha times a1 plus alpha squared times a2 plus alpha cubed times a3. In other words, exactly this expression. But here the meaning is a little bit different, because although these four things are numbers, these four objects are actually not numbers. They're polynomials, or they're vectors in this vector space that we're considering, which happens to be P3. But nevertheless, it's really helpful sometimes to think about this expression as being a product of a row vector times a column vector, where the row's elements are themselves vectors. So let's introduce some notation for that. Let's represent this row vector, which after all just reflects the elements in our basis, by the letter b in brackets. B is the name of the basis. So this is the vector whose four components are the four basis vectors in B. And this we've already seen. That's the coefficient vector of P with respect to the basis B. So this new kind of object, it's a new kind of thing. It's a kind of a vector, but its components are actually polynomials. But that doesn't bother us. We're just going to work with them as if they were numbers. The algebra still works even if these things are not numbers, if they're vectors instead. Similarly, that same polynomial, if we write it in terms of the f basis elements, in other words, the various falling powers, then we have other coefficients, b0, b1, b2, b3. We can write that product as a row vector, which we'll call f, times this column vector, which is the coordinate vector for P with respect to f. So the same polynomial has two different representations, and here's a matrix equation that represents them. Both of these are expressions for P. Here, the vector b times the coordinate vector for p with respect to b is equal to the vector f times the coordinate vector of p with respect to f. And this is a very nice equation that's valid for any polynomial p. And in fact, it's valid for any bases b and f of the space. These are just different ways of representing the polynomial p in the space with respect to these two bases. There's our vector f explicitly. All right, now suppose that we already know a relationship between the vector f and the vector b, these two row vectors. Suppose that we know that f is equal to b times some matrix C. In this case, it will have to be a 4x4 matrix. In fact, we do know such a relationship. We already wrote them down essentially on the previous page. So in other words, we know how to express the f basis elements in terms of the b basis elements, and that's essentially what this equation captures. So if we know this equation, then we could replace this f with b times c, and then this equation would read vector b times coordinate vector of p with respect to b equals now vector b times matrix C times coordinate vector of p with respect to f. Well, there's b's on both sides here. This coordinate vector had better be equal to this coordinate vector. So we deduce then that the coordinate vector for p with respect to b equals the matrix C times, on the right, the coordinate vector for p with respect to f. So if we know this relationship between the basis vectors themselves, then we know this relationship between the coordinate vectors for any vector b in the space. This is at the heart of the problem of change of basis and how it affects coordinates of vectors. Please make sure you think about this little scenario. Now we'll illustrate it in our situation over here. Here's the relationship between the two bases that we've already written down. Here are the falling powers. Here are the standard powers. This matrix, essentially the Stirling matrix of the first kind with appropriate minus signs. So like a signed Stirling matrix of the first kind. What we need to do now is to take this expression and convert it into a relationship between row vectors. Here we have a column vector equals a matrix times another column vector. We can transform that by taking a transpose. What does that mean? It means where we simply interchange rows and columns. So columns become rows, rows become columns, and a matrix like this becomes transformed into another matrix where the original columns are now the rows and the original rows are now the columns. So what happens then is that this vector transposes this vector transposes this matrix transposed is this. Let's just check that. For example, the third row here is 0, minus 1, 1, 0. The third column is 0, minus 1, 1, 0. Now, you might say, well, why did we change the order? Well, we have to change the order in order for it to make sense. So, for example, let's have a look at what alpha to the 2 falling is here. It's the third element here, so it's obtained by taking this row times the third column. 0 minus alpha plus alpha squared plus 0. That's the same content that we had here. Alpha to the 2 falling is 0 minus alpha plus alpha squared plus 0. We have to interchange the matrices when we take transposes. So this is the matrix that we're calling C. This is the vector F, that's the vector B, that's the matrix C. And so the previous formula on the previous page tells us that for any polynomial in our little space, the coefficient of that polynomial with respect to the basis B is equal to C times the coefficient of that polynomial with respect to the basis f. Multiplying by this matrix C converts from the f basis to the b basis. So let's look at an application of this. Very interesting and important application. We're going to analyze a sequence, a polynomial sequence. And this is the one we're going to analyze, the sequence of square pyramidal numbers 0, 1, 5, 14, 30, 55, 91. We may suppose that we're just given that sequence and we're asked what's the general formula, how do you compute further terms. We'll call that sequence S. Our strategy is to calculate forward differences. Forward difference triangle S, so that number is 1 minus 0, this 4 is 5 minus 1, and so on. Then triangle squared of S, the forward difference of the forward difference. This 3 is 4 minus 1, that 5 is 9 minus 4, and so on. Third forward difference, the fourth forward difference, all zeros. Here is that formula of Newton that expresses the original sequence or polynomial in terms of certain coefficients times the falling powers. And the coefficients can be computed by essentially taking these forward differences and looking at their values at 0. Put them in red right here. So it's these four numbers that are the coefficients that appear here in the numerators here. We have to divide by k factorial, and we're summing that up. Actually from 0 to, well, however many terms there are. So what are these coefficients? Well, they're just these numbers divided by the corresponding factorial. So 0 divided by 0 factorial, which is 1, that's 0. 1 divided by 1 factorial, 3 divided by 2 factorial, and 2 divided by 3 factorial. That gives us a vector of coefficients of this sequence with respect to our falling power basis, f. Now in previous video, we saw that we could, from this point, write out an ordinary expression by simply replacing all of these falling powers by the corresponding polynomials and expand it all out. And I asked you to do that for homework. Now we're going to see a simpler way of doing that same thing. We're just going to observe that the formula we've just learnt is that if we want the coefficient vector of our sequence with respect to the standard basis, we just take the coefficient with respect to the f basis and multiply it by this matrix C. There's the matrix C. There's the coordinate vector with respect to f basis. Do the matrix multiplication. That's then the coefficient vector with respect to the standard basis. And that simply means that the sequence is equal to 0 times 1 plus 1/6 times alpha plus 1/2 times alpha squared plus 1/3 times alpha cubed. All of that laborious expansion of falling powers and arithmetic to add them all up is captured for us by the linear algebra working with the matrices. By the way, this expression can take a common denominator of 6, and then somewhat happily it factors into this hopefully somewhat familiar formula. So that's actually the formula for this sequence S. And we've computed it by calculating forward differences, then multiplying by corresponding coefficient vector, which is essentially the forward differences divided by appropriate factorials. Multiply that by C, and we've got the coefficients of the polynomial in our standard basis. That is a really useful thing to be able to do. That's something that, if you're doing mathematics, you will want to do that every so often. It's a fun thing to do. It comes up in practice. So let's just have a look at this matrix C. Obviously that's pretty small. It'd be nice to know what some bigger values are. I'm going to show you the bigger values now. So there's a general infinite array. A general C goes off to the right, goes down here. It's upper triangular. And here are some of the values. If you want a particular C for any particular value of n, you're just going to take a top left square corner of this matrix. So it might be 3 by 3 or 4 by 4 or 5 by 5 and so on. And it's a nice pattern. This is really the Stirling matrix of the first kind, except that it's been transposed, and we've sort of signed it by putting in minuses on every second diagonal. Our first exercise is to calculate a few Stirling numbers of the first and second kind, and you can try to calculate those in a number of different ways. The second one is to express a particular polynomial in terms of the basis f and r, for rising now, of our space of polynomials of degree 3 and less. The third one, similar kind of thing. Now we're given the polynomial in terms of the falling powers, and we want to rewrite it in terms of the bases b, the standard basis, and the rising basis, this one here, of P3. So we want to get used to converting from one basis to another. All right, and some fun kind of projects to analyze some sequences. So these are polynomial sequences. We'll assume that they all start their indexing at 0. So that's the 0th term, the first term, second term. And I want you to apply the forward difference and the analysis that we've been talking about to find formulas for them, so that you could, if you wanted to, extend the sequences arbitrarily. So there's 1, 2, 3, 4 different ones to practice on. And the final exercise, to have a look at what we've been doing today and to try to develop an analogous algorithm where we're looking not at forward differences of a sequence, but at backward differences. All right, so see if you can go through it and figure out how we would work, how we would analyze a sequence if we could only apply backward differences. How would you recover the sequence from those backward differences? Today's lecture has been pretty challenging. We've covered a lot of material. We've introduced some rather sophisticated concepts. I think this is probably the high point of our little course here. So it's probably the hardest lecture in the subject. So if you've been able to stick with it, or if you can watch it a few times and get the hang of it, well done, you're doing really well. You're learning some important mathematics. And you're getting used to the very important idea of thinking about linear spaces flexibly. This is the heart of linear algebra in applications, is to have an open mind and a flexible approach to applying linear ideas to a wide variety of situations. It's not just cookbook recipes for doing particular tasks. Next time we're going to look at another application of our favorite space of polynomials of degree 3 or less. We're going to look at cubic splines, which are very important for forming nice curves going through points, for drawing pictures. So we're going to draw pictures with cubics next time. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.